everyone within the sound of my voice to take heart and be filled with faith and remember the Lord has said he would fight our battles. And what must we do to merit such a defense? We are to search diligently, pray always, and be believing. Then all things shall work for our good if we walk uprightly and remember the covenant wherewith we have covenanted. The latter days are not a time to fear and tremble. They are a time to be believing and remember our covenants. Okay, so you have the promise that the Lord will help you even for very stressful things like tests. Okay, so you can pray, you can have the Spirit bring things to your remembrance, and you can have the Lord comfort you. All of those things are good. Okay, so for today, we're going to go ahead and work through as many of these review questions as we can in class. Thank you to those who completed the responses, so that we can make sure we hit ones that are most popular or most questions about first. Okay, any other questions about the exam? Format wise, length wise, it's about the same as the previous exam. What other questions? Anybody think of? The material on the back of the exam. Is available under the exam preparation material. Ones that were very popular for us to review are these last four from last time. Okay, well, the last three. So the understanding the advantages of storing and transmitting a signal as a digital file instead of analog. Okay, those were on your handout from last time. Okay. They're also in the slides. They include less susceptible to noise, better error correction, more dense storage, and larger dynamic range. Okay, and then we have these three. Calculate the bit rate, know how the choice of sampling frequency and bit resolution affect the digital signal, and then calculate the total storage space. So we're going to go ahead and go do some there are some examples of those. All right, so number 38 is bit rate. Okay, so bit rate is the number of bits per second that are transferred or that are being recorded or whatever. And that is equal to the sampling frequency or the sampling rate. Those words are synonymous. Times the number of bits per sample, which is also the synonymous with the bit resolution. Okay. So for example, and then there's the one other caveat that then you also have to multiply by the number of channels, which is 2 if it's a stereo signal. Okay, does that make sense? Do we remember that? Okay, so let's do an example. Okay, let's say you're doing a sampling frequency, okay, of 10,000 hertz. So it might be written as kilohertz, right? You have to remember that that's thousands of hertz. Okay, and let's say we're doing 8-bit numbers or 8 bits per sample. And we're recording in stereo. And you're asked, what is the bit rate? Okay, and then you would multiply those all together. So you would have 10,000 hertz, okay, which is samples per second, times 8 bits per sample, times 2 channels, because this is samples per second per channel, and then 2 channels. Okay, and the samples will units cancel, not the seconds. And the channels will cancel, and then you would be left with, if you multiply all those out, 160,000, I believe, bits per second. Any questions about that? Okay, and then number that was 38. That's 38. Okay, number 39 then is about what happens. Okay, so if the sampling frequency is increased, what happens? There are two things that happen. Okay, one is the highest usable frequency, might say audio frequency, will go up, and the storage size of the file will go up. Okay. And then if the bit resolution or the number of bits per samples goes up, then the granularity of the amplitude, like how many different amplitude levels you're encoding, increases, and this file size or the storage size also increases. Yes, please. Okay, so let's look at it. So if you come here under exam preparation materials, right? These are the ones I'm using. There's also this older one that you should not use. I need to hide that. This is the current one. Okay. Does that help? Thank you for bringing that up. Okay. Are those last questions not the same on the other one as on this one? But those are different. Okay, good. Okay. Thanks for asking. Okay, and then number 40 is what is the storage space? So we'll just continue our same example here. Okay, let's say you have this same signal, same recording process you're doing in stereo, but you want to go for 10 minutes. And then the question is, what is the file size that's going to result? So the file size is that bit rate that we found above times the time, but that time has to be in seconds. So if I have my 160,000 bits per second, I have to multiply that by 600 seconds. Okay, because 10 minutes is equal to 60 seconds. Because in 1 minute, there are 60 seconds. So that would give me 600 seconds. So then if you multiply that out, then you get just the number of bits. Questions about that one? Yes, please.
Sorry, I have a question. Going back up to 38.
Yeah.
So if you go, sorry, if you look a little bit more, what is like the number of bits per sample and like the bit resolution? Are you multiplying? It's like in that top corner.
Yeah, so this is a multiplication sign. Is that what you're asking?
Is it multiplying from like that situation, like it's continuous and like the bits over second? Or that's inconsistent?
These are equivalent statements. Thank you. They're both definitions of the bit rate. Just one is using more like variables and one is using more like words. Yeah, they're the same statement.
So is when you wrote number of bits per sample, is that like the definition of sample?
Bit resolution.
And so then the number of questions. Oh,
Yeah, and then if there are two if it's stereo, then you have to multiply that by 2. Oh, I wrote a pound instead of the 2. Oh, no, that meant number of channels. Multiply by the number of channels. So multiply by 2 if it's a stereo signal, which is where this guy came in. Okay, good. Other questions about that? Please ask questions. Did that answer your question? about that. Thank you. All right. Okay. Sounds good. All right, we're gonna go back up to the top. Look at 7, 9-ish, 9 to 13, and then 20 to 23. Okay. Okay. So if we come back up to the top, okay. Someone did ask about the parts of the ear. That's that same diagram that is in your book, but you don't need to know the cartilages. The name of the cartilages, but the others you do need to know the names and what they do. And then remember that on the basilar membrane, the part that's by the oval window is the high frequencies, right? So that would be like 20 kilohertz would be like all the way over here. And then 20 hertz would be all the way over here. But the high frequencies are closer there. All right. Okay. All right. So number. Okay. I think we said 7 through 9. Does that sound right? Okay. Does anybody want to see? Does anybody want to see the whole like Sones, Fawns, levels thing? You want to review an example of that? Okay. I think it's helpful, so we'll try. Okay. I don't remember what number this is. It's roughly 6. You can tell me if it's really number 6. Okay. So what loudness in Sones corresponds to 2000 hertz at, oh no, let's do 4. 4000 hertz at 73 decibels. Remember roughly doing one of these 2-step problems? Okay, so what is the first step? The intermediate from going from decibels to Sones. What do we have to find in between? The Fawns, right? Okay, so we start here on our graph. We find 4000 and we go up to 60, that's 80. So 70 would be in the middle. Okay, so if I come up to 4000, let's say it's on that line right there. Okay, but that corresponds to the 80 Fawn line. Right? Okay, so first thing is to say the loudness level for that is equal to 80 Fawn. And then you look at the table to find out what the loudness is. So that's this table right here. So I would find my 80 Fawn line is where I was. So that would correspond to 16. So yes, please. Yeah, for the test, it will not be lower than 40. It will only be those ones that are on the test. This table, this is the table that's on the test. So it will only be these. Okay, good. Questions about that? Yeah. Is that number 6? Did I get the right number? Okay. Other questions about doing that? All right, let's see. Okay. All right, so number 7 says When given 6 simultaneous sinusoids of specified frequencies, determine the fundamental frequency of the pitch that would be displayed, okay? So can you see that green well, or should I go to a darker color? Okay. So for example, let's say that I was given 50, 75, 125, 200, 225 hertz. So that's 6. So I got to do one more, 275 hertz. Okay. And then I was asked, what is the perceived pitch? What would be the answer? Yes, please. It's not the lowest. That's the tricky thing. Is that it's not the lowest. It would be the lowest except for one thing, the tricky thing our ears do. 25. Okay. So if all of those numbers are multiples of something, the perceived pitch is that something. Okay. So these are all multiples of 25. So the perceived pitch will be 25 hertz. That's called filling our brains, our ears, filling in the missing fundament.
Is it all going to be relatively simple math, or are we going to do like multiples of 13?
So what, yeah, I can't remember exactly. So I can't speak to that, but consider the differences, right? Like, and notice it doesn't have to have all of them, right? Like it's missing 100, it's missing 150, 175, right? But just take your differences between a couple of them and see if that difference, if you divide all the other numbers by it, does it happen to be that, right? And maybe any that look relatively close, right? There might be some bigger gaps, but look for the ones that are close, find the difference, and then divide the other numbers by that and see if that's your answer. Does that help? Yeah. So pitch is what the note on the piano that we would call something. So 25 hertz is really low for our ear, but it's easy to do the math. So that's why I did that example. But so the pitch is, you know, if I play the A on the piano, right, that's A 440. That means that pitch, what we would call that note, is 440 hertz. But there are lots of different partials in that. In that case, it is the lowest one. It is the first partial. This is just a very special case where if it's missing the fundamental and other things or multiples of it, our ears will fill that in. That's why you can hear lower frequencies in your headphones, that the headphones are not actually producing your earbuds. They're too small to really produce bass. Okay, but if it produces the partials above, then our ears will fill in that missing fundamental. So you get bass on something that isn't actually producing it very well.
I remember we talked about like 2 formulas, there was like F2 minus F1 and like 2 F1 minus F2.
Yes.
Is that what this is? Or is that
No, so that's number 8 here. Okay, so good question. So this is number 8, is a little bit different. So number 8 is other frequencies that our ears will introduce due to nonlinear response in the ossicles and in the cochlea. These typically are only observed if they're very loud and if it's 2 sine waves that are put into the ear. So there are 2 possibilities here. One is the lower plus the higher. Okay, that would be the most likely. And then the other one is, oh, sorry, difference, right? Difference. Sorry, thinking of something else. Okay, higher minus the lower is the most likely, and 2 times the lower minus the higher is the second most likely. Okay, so if, for example, if you had 500 hertz and 700 hertz being played loudly in your ear, the most likely one that you would hear would be the difference, 700 minus 500. And if that's not on your answer list, then the second most likely would be 2 times 500 minus 700, which would be 300. Okay, where this is F1 and this is F2.
So what's the difference between, I just thought that concept was 10. What concept is different?
Oh, Sorry. Sorry, it is, you're right. I saw simple tones and got confused. That is number 10. That is number 10. Okay, sorry, that is number 10. Okay. Number 8, sorry, number 8 goes with our just noticeable differences table. Okay, good, sorry to confuse you. This really is number 10. I just didn't read carefully enough. All right, but number 8 has to do with our just noticeable differences table. So I'm going to actually put it right here. All right, so for number 8, this is where, will two simultaneous, meaning played right after each other, tones, meaning their sine waves, sound different, be perceived as different. Right, that's number 8. Okay, so we keep straight on the numbers. Okay, so this would be, for example, so for 2 tones at 800 hertz, if the first is at 60 decibels, oh no, that's not on our chart, 40 decibels, what level for the second will be perceived as different? Okay, so the first question is, you have 2 tables here that look almost identical. How do you know which ones to use? Okay, and the key here is, if you're wondering about levels, use that one. That's this purple case that I'm doing here. And if you're wondering about frequency differences, then you use the frequency chart. Okay, so for this one here that says it's 4 intensity levels in decibels, that means that all of these little elements in the table have a dB by them. Okay. Whereas on this one, the frequency in hertz means all of these guys have a hertz by them. This would be too crowded to write them all out. So that's the first thing you have to know. Any questions on how to know which table to use? All right, so for this specific case, we're talking about intensity. So then you find the frequency you're talking about, you find the level that you're at, and then you identify there has to be at least a 0.93 difference, decibel difference. Okay, so that means that I would take my 40 decibels and then I could add the 0.93. So then I could say the level would have to be greater than 0.93, or I could subtract and say that it has to be less than 39.07 dB. So greater than that one or less than this one is when you would perceive it as a different loudness, where you could say, oh yeah, that was quieter or louder than the first one. Questions? Yes, I will post. If I forget, email me. But I intend to post. Okay, do you want to see an example with frequency, or are we good on that one? Okay. All right, so let's go see what's next. Okay, how about 9? How are we on 9? Okay, on 9. All right. 11 and 12 are good ones to practice. Oh, sorry, I didn't hear you. Okay, 9. Okay, so low frequencies, right, depend on the phase of the waves. because the head is relatively small compared to the wavelength, and the high frequencies, it is the intensity. All right, I think 11, 12, 13 are good to do. Wrong one. Okay, now I have to remember what. Okay. 11. Okay. All right, so this was from table 1, was that one? Okay. All right, so number 11, I think, is that the one that says how long do you have to hear something to tell a pitch? What number was that one? 11, 12, 13, it's one of those? Okay, 12. How long to distinguish pitch? Of a 1000 hertz tone. Okay. So for that kind of question, you're going to be looking at this table here, which is table 4. The heading is just at the bottom of the other one. No, it's not. It's table, that is table 4, but table 5 is the one we're using. Okay, so table 5. And then you find 1000 hertz and you say it has to be heard for 10 cycles. That's the number that you need off of that. Okay, so from table 5, you need to hear 10 cycles. So the total time that you need to listen is going to be the number of cycles times the time for one cycle. And that time for one cycle is equal to the period, which is 1 over the frequency. We're doing that. So this turns into the number of cycles divided by the frequency. So that would be 10 cycles divided by 1000 hertz, which would give us 0.01 seconds, which is the same as 10 milliseconds, because you move 3 decimal places over. For milli, it's 1000. You divide by 1000. Okay, questions? Yes, please.
Number of cycles into multiply it by.
Which is the same as dividing by frequency. So this is kind of an aside over here. This is just a remember that. Using that fact I get from here to there. This. Oh, no, from table 5 here, I got the number 10 cycles. Okay, yeah. Good to clarify. Okay. Okay, questions on that one? Okay, what does number 11 say? I wanted to do that one, but I forget what it says. Oh, beating, that's right. Okay, so we'll, whoops. We need more room for this one. Okay. So number 11, okay? This has to do with this lovely chart that we had, right? Where there was F1, F2 varying from F1 to F1 plus a critical band. And then this axis was the perceived pitch. And that kind of went, and this was F1. And that went just as was hearing one thing, right? Until you got to that critical band, and then it would break into 2 tones. Okay. So the perceived pitch, there was just one pitch when F2 and F1 are within a critical band, and then 2 pitches after. Okay, and then if the difference, the beat frequency, if the difference was less than, say, 10 hertz, then that yielded smooth beating. And then if it's greater than 10 hertz, but less than a critical band is the difference, then you're going to get rough beating. We're not going to worry about that whole quarter of the critical band thing. That was just so you could understand, but this is what you're just doing. Okay, and then if the difference is greater than a critical band and we're not thinking about higher harmonics, then you will get no beating. And you also get no beating if they're the same pitch, if they're exactly the same pitch. Questions about that guy? Yes. What does number 8 say? Can you read it too? Yeah, so number 8 is this one. It's where you're doing your just noticeable difference tables. You're not talking, and these are played. So actually, these are not simultaneous. These are consecutive. Sorry. Can't spell today. Sequential. We'll go with that one. I can spell that one today. Okay. So this is like da, da. Like, what's the pitch different? As opposed to da, da. Whereas this one is you have two of them played together. What is the perceived sound quality? Is it smooth, beating, or rough? Good question. Yes.
So is that F1, F2, going to be given to us, or find out the graph? And if it's on the graph?
Okay, very good question. So if there are numbers on your graph, say if instead of F1, it said 250 there and 302 there, okay, then you would understand from that's a difference that the critical band was 52 hertz. Okay, but you'll be told, you know, if you have this frequency and this frequency, you'll either be told this frequency with this critical band, or looking at this graph, this frequency and find the critical band. I can't remember which one it is. Yeah.
So we're not going to be tested off like the whole quarter.
No, we're just going to simplify it to this for the exam. Okay, good. Yes, please. No, we won't be doing anything with the 1/4 of the critical band. I made sure the critical band was larger than 40, so it's not. So 10 is not close to the critical band, quarter of the critical band. At the low frequencies, that 10 doesn't work as well, but we'll just stick up above that. Okay. Okay. All right. What was number 13? Can someone read me number 13?
Know how to read and interpret an audiogram and view it, what
Great.
needed at this specific frequency control.
Thank you. Okay, so number 13 is talking about audiograms. Okay, so if on an audiogram, this is the 0 line, right? And then we have our different frequencies. We'll just look at 500 hertz today. Okay, let's say at different frequencies, at 500 hertz, this person had 40 dB of loss. So their X or O was right there. Okay. So that X would correspond to 40 dB loss at 500 hertz. This maybe is a temporary threshold shift after an accident or something, right? Okay, and then the question is, how much amplification needed to restore normal hearing? So normal hearing is this line, right? This line right here. So how much amplification would you need to restore normal hearing? 40 decibels. That's one kind of question. The other kind of question is, with this loss, what is the lowest sound level they can perceive? So that's a different question, right? And for that, it may be 13 or it may be something else, I'm not sure. Okay. So then you have to take your 40 dB and your 500 and go to these equal loudness contours. So here we have our 500 The plus is normal threshold. A loss of 40 decibels means that I have to go 40 above this guy to find the lowest level the person could hear. So if we assume that that's around 10, I would add 40 to that and get 50 as the lowest level they can hear. I don't know if that is also question 13 or if that's a different question about temporary threshold shifts. What one is that?
14.
That's 14. Okay. All right. How are we doing? Okay. Let me see if I can. That way. All right. Okay, then we have another bunch here around 20 to 23. So let's go to that section next.
Just for number 13.
Uh-huh.
It said, what are the common types of hearing loss?
Oh, sorry. And so this wasn't number 13 at all.
No, it's like both of them.
Oh, sorry. Okay. Okay, good. Okay, so another part of 13 then is the common hearing loss question. And what would that look like on the audiogram? So common hearing loss with age, right, would be presbycusis, where somebody's maybe kind of in this as they age, right? They've got something kind of going on like this, and then it goes, right, it tanks at the high frequencies. That would be the loss of low frequency hearing. Is called presbycusis. That is the most common form of hearing loss, and that's what it would look like on the audiograms. A real roll off there. Anything on this?
Was it the low frequencies or the high frequencies?
Sorry, loss. Oh, yes, I wrote it wrong. Thank you. High frequency hearing loss. Good. All right, so let's now look at 20, 21, 22, 23, kind of these guys. Oh, yes, sorry, back on 13
Yeah, in lecture you mentioned that when they are amplifying, like, say they're using hearing aids to hearing,
in practice.
you just amplify those to 20 level, right, rather than 0 level. So with that question, when it's saying like how much do you need to amplify to restore the person's hearing to normal, are we saying normal as in 0, or are we using the like application and how much does it take to get to normal?
Yeah, the 0. Yeah, for the exam, we'll do the 0. But in real life, they don't do that, but it's just easier to just say that's what we're going for. Yes.
So going up. to 30 decibels.
Well, so this one is more like, how do you read an audiogram? Remember how we had like those qualitative statements of the left ear hears right better than the right ear at 1,000 hertz, those kind of things. 13 is more reading the audiogram and making statements about it. Right ear has common hearing loss, the left ear has some weird low frequency stuff that's not common. So 13 is really about reading audiograms. The one, this temporary threshold shift is really number 15. So, does that help? Does that answer your question, or is it a different question? They're connected, but they're just, one is just like reading an audiogram. How do you interpret an audiogram?
When you did that example, was it for which network?
So, oops. So this first part was 13. And this second part with this up here was 14. Say again. Sure, we'll do another example of 14. Okay, so let's do another example of 14. Let's say someone experiences a temporary threshold. So first you assume normal hearing before some exposure. Okay, and then you say, okay, let's say they have a temporary threshold shift of, we'll just say 30 decibels this time. Okay, And then you have to say at what frequency. So let's do 8,000 hertz. Okay, and then you want to know the lowest sound level they can hear. Okay, so here I come to 8,000 and I find the plus, that's my starting point at a roughly 10. And then I need to go up 30 from that, which would take me to 40 decibels. That help? You see? Yes.
So then the answer is just where you don't do anything with the phone.
Right, you could figure out the fonts and the sones, but that's a different question for right now. But they do all come together, right, when if you are an audiologist, those are all connected. But we will approach them separately for the test. Yes, please. Yes, so if in the context of question 13, the amplification to return to normal hearing threshold would be 30 decibels. Good. Okay. Questions about that? Okay, these are good questions. Now, just real quick before we get to the end, if you have more questions, you're welcome to meet with our TAs. Kayla will have office hours, I believe, starting at 5 today in C460, the lab room where most of the labs are. Caleb tomorrow from 4 to 6, and then Emma at 11 on Friday. Okay, so just they don't have anything prepared, just bring your questions and they can work through them. Okay, so what causes the glottal opening to change its size, change its area? Okay, so the glottal opening, first of all, that is the space between the vocal folds. And then it opens when there is positive pressure in the glottis from the air coming up from below, and it closes due to negative pressure in the glottis from the Bernoulli effect and the tension in the vocal folds. Just the natural restoring force like on a rubber band. Describe, number 21 says, describe the wave shape and spectrum of the air flowing through the glottis when typical voice speech sounds are produced. Okay, so it is periodic, right? Periodic motion for voice speech sounds. That motion creates a periodic stream, which means it will have many harmonic partials. Number 22 is talking about our neutral vocal tract. Okay, these would be like the vocal folds down here. This is our sound that we can model as a closed open tube. This would be the lips up here. Okay, and so this is a tube of length L. So, and this is an open closed or closed open, however you want to write it, tube. So the fundamental frequency of an open closed tube, which in this case are the formant frequencies, not the partials, but which of those get amplified by the resonances of the vocal tract. The V would be the V over 4L, and F2 would be 3F1. Questions about that? So now again, I lost the number. I keep forgetting the numbers. Thank you. So we have formant 1 for that open closed tube is V over 4L. Okay, and then F formant 2 is 3 times formant 1. So if the length increases, what happens to the formant? The length is on the bottom, so they would decrease. If the wave speed increases, then what happens to the formants? Will increase. And if it changes shape or cross-sectional area from the, to something else, right? And some formants are gonna go up and some are gonna go down. But you'd actually have to do the modeling to figure it out. Yes. Sorry, what? Oh, it's really number 22. Thank you, sorry. For some reason, my brain is not holding on to those numbers every time I switch screens. Oh, or 23? Okay, sorry. All right. Okay, your brains are probably very full. Okay, we're basically done. I will post both of these. If you, I don't care if you take these papers or not, you can practice, but if you did not get one of these purple sheets, it's on the exam review materials packet, but this is just how the phonemes are going to be represented on the test. Right, whether we, it's a word example for each of those, so that we can help, hopefully help with that. Okay, let me know if you have other questions. If you want to do the extra credit with the earplugs, you're welcome to come get some. And good luck on the test.